Welcome to this NPTEL course on Advanced Pre-Stress Concrete Design. In this week, we are moving into the module 5 and we are going to talk about analysis and design of shear and torsion. Quick outline, the expected learning outcomes after the student goes through this part of the module will be able to identify the crack patterns and failure modes, particularly in pre-stress concrete beams, and able to explain how pre-stressing actually modifies the shear behavior, or I should say shear resistance of the pre-stress concrete beam, and understand the design methodologies for shear and apply the IS 1343 code provisions for shear design through a worked example. Right. So, we all know that typically the beams are initially designed for flexure and then they are checked for shear. For example, you see here you have a simply supported beam which is subjected to some uniformly distributed load and a concentrated load. If you take this section and take the free body diagram, you will have both bending moment and shear. So, in this case the axial force is 0. So, your section will be subjected to only shear and bending moment. These are internal forces. We need to design for these internal forces. So, first we design the section for bending moment. Again, most of the time for a beam, the dimensions of the beam are controlled typically by strength requirements. If they are longer, then the deflection will govern the design. For a pre-stress member, typically we go for pre-stress for long beams, then the depth requirement is governed by deflection, but if it is for reinforced concrete without pre-stress, typically the strength will govern the depth of the member. Right. So, for the bending moment, first we come up with the reinforcement requirements, typically the flexural reinforcement, the longitudinal bars are designed for. But however, in addition to that, you also have shear that is acting in this cross section, right. So, we need to make sure that the section that is designed is also going to be sufficiently strong for the resisting the internal shear force that is being developed. Now, so whatever the cross section dimensions that we came up with for flexure, we designed them with longitudinal bar. This is for flexure or bending, right. Then whatever the dimensions that we came up with, we need to check for shear and to make sure that it is not going to fail in shear. If the concrete capacity is not adequate, then we go ahead and design the shear reinforcement, if required, or if it is not required, then we do not put the shear reinforcement, depending upon the level of conservatism that you have between the concrete shear capacity and the shear demand, right. So, in general, we design the element for flexure first and then we design it for shear. That is the process. Okay. Now, shear effect or can be more significant than bending as well, right. So, for example, you see here there are there is a pre-stress box girder bridge that you see here, and you see all kinds of cracks. Okay. You see here this is close to 45 degree, or I should say this is close to 45 degree, right. And you see right in the middle, you see this nice flexural cracks, right. But in between you see here you get this flexure and then it goes like this. So, these are called flexure shear crack. Okay. So, this is a web shear crack. Okay. So, depending upon the type of the crack and its pattern, we can identify whether it is governed by flexure or shear or combinations of flexure and shear. Typically, when the beam tries to fail in shear, usually it is initiated by the diagonal tension, which is actually far more dangerous than the flexural failure due to its brittle nature. So, what is the meaning of that? If the section is weak in shear, then it can fail in an abrupt, brittle manner without any warning. So, that means for any given cross section, we make sure that the capacity in shear is always higher than the demand, and we always want the section to fail in flexure or bending before it can reach its shear capacity. So, the weak link has to be always flexure dominant behavior for a beam. Now, beams are generally provided with special shear reinforcement to ensure that flexural failure would occur before the shear failure when they are severely overloaded. That is what I said. Typically, we make sure that it is failing in flexure by making sure that always the flexural failure will govern the design, not the shear failure. Okay, so let us look at it. We understand how the uncracked beam, reinforced concrete beam, is going to behave in shear. Let us take this simple beam and it is subjected to 2 point loads in the middle. Now, for this beam, let us see what kind of shear force and bending moment diagram that I am going to get. So, we know that from basic statics, right, you know how to get your shear force diagram. You get shear is equal to applied load, and in this region no shear, right, and it is a pure bending region, and this is your bending moment region. Now, for any cross section that I choose, I will have both shear and bending acting. If I am taking a cross section here, you see here only bending moment is there, but shear is 0. So, that is why it is called as pure bending region. But if I am taking a section here, my bending moment is less, right, here bending moment is less, but shear is high. So, close to the support, it typically that is the reason you will have shear dominant behavior, but in the midspan regions typically, you know, unless you have point load kind of distributions, you will be governing by bending dominant behavior. Okay. Now, let us look at it. How the shear stresses and bending stresses. We know how to get the distribution of my bending stresses. We know that sigma is nothing but m by z, moment at the section divided by the section modulus, or you can say that sigma is equal to m by I into y. Y is the distance of the fiber from the neutral axis. So, we can calculate. So, you get all your stresses, right, and you get this. So, this is in compression, this is in tension, and so on. Now, how do we get the shear distribution? Shear distribution from your basic strength of material, we can get it from this formula, which is your shear in the cross section times the Q divided by I by B. Now, Q is your first moment of area above the neutral axis for the portion of the section above the layer at a distance y from the neutral axis. So, what does it mean? So, if I am trying to calculate at this distance y from the neutral axis, I calculate this area and then I take the first moment of this area. So, that is what the Q is, right, and B is the width of the beam. Okay. So, if you do that, at this point you have 0 shear stress, here you will have maximum shear stress tau max, and here it is 0, right, it is a parabolic variation. So, we know that from this variation from the strength of material course. Now, in reinforced concrete, what we really do here is we try to take an average shear stress, which we call that as a nominal shear stress. So, because concrete is neither elastic, right, so it is not exactly it's a highly nonlinear heterogeneous material. So, you will have lot of redistributions. We take what is called as an average shear stress and we average them and we calculate that for our calculations, use it for our calculations. So, V max is typically the maximum shear stress is 3/2 of the average shear stress. You can see that. Yeah. Okay. Now, what are the shear transfer mechanisms that you have? If I take a cross sections, you can see that if you take only 1/2 of a beam that is already cracked in flexure and then shear, you have this kind of a cracking that has happened. Okay, and you see only if I take the free body diagram of this element, to resist the applied internal shear, you will have contribution that is coming from your uncracked concrete in compression. And then we have, for example, this is a pre-stressing strand, and this is your normal non-pre-stressed steel I should say. Okay. And depending upon the crack, how much distance, typically we assume this crack to be 45 degree. So, this horizontal distance over which this cracked portion is going to cut the number of stirrups will be within the distance d. So, all the stirrups what we put will be subjected to, at ultimate condition, it is assumed to reach yielding. So, the maximum tension force that I am going to get will be the area of the stirrups multiplied by the yield strength. So, that is the force that we are seeing. And if you look at this, you have multiple forces that are here, and this is your pre-stressing force. We have tensioned this pre-stressing cable. So, you will have, as we have discussed in the previous lectures, you will have horizontal component of pre-stress and a vertical component of pre-stress, right. So, we know that this is the distributions. So, now if you look at it here, you have multiple things that are contributing to the shear resistance. What are those? Now, this VCZ, which is your uncracked concrete in compression, and between the cracked elements, if you see here, okay. So, at this interface, if you look at it, when it is, let us say, it is subjected to loading like this, it is having this kind of a failure. Now, between the cracked surfaces, the crack is not going to be smooth and it is going to be rough, because your aggregates are going to be there. Now, typically aggregates are stronger in a normal concrete than cement paste. Okay. So, what will happen is the crack will go around the aggregate. So, now at the interface, now I am going to have something called aggregate interlock, which we call that as VA here. Now, that VA, if I take it, this VA will have two components. Okay. One is this vertical component, which is VAY, and there is a horizontal component, which is VAX. Now, for shear resistance, the vertical shear resistance, there is going to be a component, the vertical component of the shear, that will be transferred across the crack by interlock of the aggregate particles between the two faces of the crack, because the surface is not going to be smooth. So, when shear force is acting, there will be lot of shear that will be transferred across the interface between the crack, when the crack widths are very, very small. If the crack widths has become quite large, obviously that VAY component will become 0, but when, because we are also going to put lot of stirrups, at ultimate, typically the crack widths are not going to be that high. So, still there will be some resistance that will be offered at the interface. So, that is why the code is adding these two things, VCZ plus VAY is considered in the shear resistance. Now, there is also one more component called VP, which is a vertical component of the pre-stressing force. You see here, this is what we are saying, VP. So, if you sum this thing up, you have, the total shear resistance, if you look at it, I have VCZ plus VAY plus VP. Now, the VP is also, the vertical component of the pre-stressing is also helping me in resisting the shear. Okay, these are the things. Now, if you look at only concrete components, the VC can be taken as only two things, which is VCZ plus VA, where VCZ is nothing but your uncracked concrete contribution in shear. That means, whatever that is above the crack, that uncracked portion, that will have its inherent shear resistance, that is what it is. called as an uncracked concrete in compression.